In this lesson, I'm going to introduce you to something that's actually central to the whole study of calculus. I'm going to introduce you to the derivative. Now, the derivative is something we define with respect to some function. So let's start with the graph of some random function. Now, to just get the definition right out of the way, the derivative is concerned with finding the gradient of the tangent to this point right here. However, doing this is actually a little bit problematic, because the tangent only really touches the curve at one point. Sure, it's also true that we could continue the tangent and it would touch later on, but finding this point of intersection over here is going to be really difficult because, again, we don't know the slope of the tangent. So that means finding this gradient is actually going to require us to be a little bit more clever. To understand the central idea that calculus is trying to show us, I'm going to go ahead and zoom into a tiny region around this x value. Now, once we do actually zoom into the function like this, we notice that the tangent and the original function at the back are almost completely indistinguishable from each other. Now, on its own, this observation isn't actually enough to help us find the gradient of the tangents. However, if we actually go ahead and pick a point on the curve that's a little bit further away, this actually will help us find the gradient of the tangent. Now, when we go ahead and add on the secant over here, if we go ahead and look at its zoomed version, we notice that it actually doesn't look anything like the tangent or the function. However, if this point that we're using to draw the secant gets closer and closer to the original point, we're going to notice that the gradient is also going to get closer as well. Now, just by looking at this, and by looking especially closely at the zoomed in version, when these 2 points get very close together, we notice that the secant, the tangent, and the function all seem to look exactly like one another. Now, to help us talk about this properly, let's actually label the distance between these 2 points as change in x. If that's the case, then this distance over here is just going to be x plus change in x. Now remember, when you substitute x into a function, it's going to give you the height of the graph over here. So the height of the graph is f of x. And then similarly, the height of the graph over here is going to be f of x plus change in x. And now we're ready to explain the idea in the most general way. We're saying that as change in x approaches 0, then this secant, this tangent, and the function will look exactly like each other, as we can clearly see in the zoomed in version. Now, to define the slope of the tangent, we're going to define it as a small change in y over a small change in x, and we write small change with the little d. Now, one thing to note is, dx and dy are both going to get very, very close to 0. However, if you actually divide dy and dx, as you make dx smaller, you're actually going to notice that it approaches an actual number. So therefore, we're going to say that the slope of the tangent is going to be called dy on dx. Now, the slope of the tangent is exactly the same thing as the derivative, and we define it as change in y over change in x. We can also write it in terms of the function f. The dash over here indicates that we're looking at the slope of the function and not the value of the function at that point. However, as we already said, the slope of the secant will also approach the slope of the tangent as change in x goes to 0, so we can write this as well. Now, because we're talking about the slope of the secant over here, it's actually going to be helpful to actually find its slope. So to do that, let's draw a triangle underneath it. Now let's label the height of the triangle change in y, since it's the amount that the y-coordinate changes. And therefore we can say that this slope of the tangent is equal to the slope of the secant in the limit where change in x approaches 0. Now it turns out that there's also another way to write this. We can say that change in y is the same thing as f of x plus change in x minus this height over here, which is just f of x. So we can replace this over here as well. This formula over here is arguably the most important formula in calculus. We call it the first principles definition of the derivative, dy on dx. Now there's actually something pretty interesting about this definition. You've got these two values that are getting so close to each other, and then you're dividing them by a value that's getting very close to 0. This immediately tells us that finding the derivative requires you to think about what it means to divide 0 by 0, and that's a little bit of a weird thought. However, I'd like to show you that this actually does lead to proper answers, so let me go ahead and show you with an actual example. Let's pretend for a minute that I was building a little bit of a skate ramp on the side of my house. So imagine I started off with this picture of the side of my house. The first thing to do would be to actually sketch on the skate ramp that I plan to put up. Now you're looking at your proposed ramp, and you're not so sure whether the slope here might actually be a little bit too large. So the first step to figuring this out is finding a function that predicts the height of the skate ramp as a function of the distance from the left wall. Now this function looks a little bit like a cubic, and if we actually play around with our graphing calculator for a while, we're going to notice that it actually roughly obeys the following formula. Now let's suppose for a moment that we wanted to check the slope at x equals 1. Now since we've chosen x to be 1, we're going to want to find what f of 1 is equal to, which we can do just by subbing into the formula. So to do this, we replaced every instance of x with the number 1. Now of course, 1 to the power of anything is just 1. And also, anything times 1 is also 1, so we can replace that too. Now you can also see that minus 1 minus 2 plus 3 is just 0. And so that means f of 1 is just 2, which is exactly what we see when we look at the graph. Now the next thing we're going to want to do is we're going to want to take the limit as change in x approaches 0. Now doing this in general is something we're going to study in a lot more detail later on, but for now let me just pick a really small value of change in x. Let's suppose that change in x was just a really small number like 0.001. Now that we've chosen a value for change in x, we want to find f of x plus change in x. Since x is 1 and change in x is 0.001, then we can say x plus change in x is the same thing as 1.001. And now, to actually find f of x plus change in x, we're going to want to sub in 1.001 into this function again. Now as we said before, this corresponds to picking a point that's really close to the point we started with, and then drawing a secant between them. The gradient of the secant should be the same as the gradient of the tangent. To actually find the gradient of the secant, we're going to want to know the value of this number over here. So let me go ahead and plug it into our calculator. So as you can see, because our change in x is so small, then the value we got is very similar to the value we had at 1. Now that we know this, we actually don't really need this calculation over here, so let's get rid of it as well. So now we want to turn our attention to actually finding the slope of the derivative at this point. Now we haven't really taken the limit here, but we've just chosen a really small number. However, we can at least say that the derivative itself is going to be approximately equal to this slope inside the brackets over here. If we go ahead and replace these for all the values that we found, and then we put this all into a calculator, we find that the derivative is approximately equal to 0.999. Now if you continue to add more zeros here, making change in x smaller and smaller, you'd actually notice that dy and dx eventually approaches 1. And now a slope of 1 implies that for every unit we go across, we have to go up by 1 unit, so the angle is approximately 45 degrees. Now an angle of 45 degrees for a skate ramp is a little bit large, so you might want to rethink this one. We can also rewrite the derivative in this form over here as well, so we can say that f dash of 1 is also approximately equal to 0.999. This sort of points us to the idea that we could use any x coordinate and find the slope at any position we like. So in a sense, this f dash over here is actually a new function that takes in an x coordinate and actually spits out the slope. Most of the time, the slope is not going to be the same as the height, so f dash has to be a different function to f. So notice that we actually have a new function here. We put in 1 and we get out 0.999. The original function f I can also draw above. For this original function, when you put in the number 1, you get out the number 2, and that's definitely not the same thing you get when feeding it through f dash. You get 0.999 instead. Now this actually completes our example, but we should also talk about this f dash just a little bit more. So far, we've discussed the concept of a derivative and how it's related to the slope of a tangent and a secant. But to really understand them properly, you're going to really want to think hard about why we're bothering to redefine this as a new function f dash. We'll talk about this a little bit more on a new page. Now first off, we already said that we can define the derivative as f dash x. Now the definition on the right hand side was really useful to actually help us calculate derivatives. But the definition on the left tells us a little bit more about exactly how they work. First off, I want you to remember that y is the same thing as f of x. And this means that we can rewrite this in the following form. Now, at the risk of abusing the notation just a little, I can also move the f of x out to the right. And this allows us to actually see the derivative in a new way. In a sense, you're taking this function f of x, running it through the derivative, and then you get this new function, f dash x. The new function f dash x gives you the slope of the original function at any point x that you want. So therefore, the derivative is actually a new kind of object. It actually takes in a function as the input and gives you a new function as the output. So it's kind of like a function, but it actually takes functions in as inputs and gives you functions as outputs. Now in math speak, any object that takes a function in as the input and gives a new function as the output is called a functional. So derivatives are functionals. Now I really think it actually helps to have a picture of this, otherwise it's just too abstract to make any sense. So let me go ahead and draw a picture. Now I've drawn the original function f as a normal box, like I usually would. The idea is that the derivative functional is going to take the function in as an input and produce a new function, as you're about to see. So as we can see, we started off with this function f, put it through our functional, and then we got this new function f dash. To make more sense of this, imagine starting off with some random x value and then feeding it through f. Of course, f is going to give you the y value. But if we put the x value through this second function over here, just like we did here, we'd actually get the slope, dy on dx, as the output. So the function f returns the height of a graph, and the function f dash returns the slope of the graph at a particular x value. I think it also helps to actually see this on a graph as well. So when you have this function f of x, you can start by choosing some random x value first. Now the first function f is going to give us the height, which is just the y value. And this second function f dash, which we call the derivative, just gives us the slope of the tangent. Now we call the process of turning this function into this function differentiating. And it's going to rely very heavily on the definition of the derivative that we gave earlier. A majority of our first introduction to calculus is going to involve actually figuring out how to convert some random function f into a new function f dash. And now I'd just like to summarize. In this lesson we showed that the derivative is just the gradient of a tangent. We said that we could find the derivative by picking some random point to the right and drawing a secant. And then we'd allow the x distance between these two functions to approach 0, so eventually the secant looks exactly like the tangent. Since we can move this x to any position we want and find this gradient anywhere, then we can actually say that the derivative is also a function, so we can also define it as this function f dash. And with that, we've completed our initial discussion on the derivative.